Hey everyone, and welcome. Today we're going to go on a little expedition, not through a jungle, but through the landscape of mathematical functions. We're going to check out the smooth roads, the sudden cliffs, and the massive canyons that make up their graphs. Let's dive in.
All right, first up, take a look at this graph. It's a nice, simple curve. Now, just ask yourself a quick question. Could you trace this whole thing without ever lifting your pencil from the paper? Yeah, of course you could, right? It's one smooth, unbroken line.
Okay, now what about this one? Try the same thing. You start tracing along from the left, everything's going great, and whoops, you hit a dead end. You've got to physically lift your pencil up, jump over a gap, and start again on the other side. That little break, that's the core idea we're digging into today.
You know, this simple little thought experiment, it actually has a name. It's called the pencil test. And honestly, it's our first and most intuitive tool for telling the difference between a function that's continuous and one that's, well, not.
And this leads us straight to our main definition. A continuous function is simply any function whose graph you can draw in one single, unbroken motion. No jumps, no gaps, no weird missing spots.
But as we've already seen, sometimes you absolutely have to lift that pencil. These breaks are officially called discontinuities. And this is where it gets really interesting, because they're not all the same. They come in different flavors, each with its own look and its own cause.
So, that's our mission for this explainer. We're going to become function detectives. We are going to learn how to identify and classify the three main types of breaks you're going to run into out there.
All right, here's our list of suspects. We've got the removable discontinuity, the jump discontinuity, and the infinite discontinuity. Let's open up the first case file on the one they call removable.
So our first type is called a removable discontinuity. The easiest way to think about this is like a tiny pothole on a road that's otherwise perfectly smooth. The road keeps going on either side, but there's just one single point that's, well, it's just missing. So the key idea here is that the function is behaving perfectly normally. It's heading towards a very specific spot from both directions, but right when it gets there, poof, the point itself has been plucked right out.
Visually, your big clue is that classic hollow circle, the hole in the graph. And where does this come from, mathematically? It often happens when you have a fraction, and a term on the top can be canceled out with a term on the bottom. That very act of canceling is what creates the hole. Okay, next on our list is the jump discontinuity. And here, we're not just dealing with a pothole anymore. Oh no, this is like a completely broken bridge, where the path coming from one side doesn't line up at all with the path on the other.
With a jump, the function is heading toward one value from the left side and a completely different value from the right side. It's just an abrupt, sudden leap from one point to another.
The visual is unmistakable. It's that sudden vertical gap. And you find these things all the time in what are called piecewise functions. That's just where different equations are used for different sections of the graph. And sometimes, those pieces just don't meet up in the middle. And that brings us to our final and most dramatic break of all, the infinite discontinuity. This isn't a pothole or a broken bridge. This is a massive canyon. It's a vertical line that the function can get closer and closer to, but it can never, ever cross.
This happens at what we call a vertical asymptote. As the graph gets closer and closer to this invisible wall, it has nowhere else to go. It just has to shoot straight up to positive infinity or dive straight down to negative infinity. It's pretty wild.
So the visual clue is that vertical asymptote. And the cause? This is what happens in a fraction when the bottom part, the denominator, becomes zero. But the thing that's making it zero doesn't cancel out with anything on top. The function is basically trying to divide by zero and it just flies off the charts.
So let's do a quick recap. A removable discontinuity is just a hole, and it usually comes from a canceled factor. A jump is a gap. You see it all the time in piecewise functions. And an infinite discontinuity is a vertical asymptote caused by a denominator hitting zero. Simple as that.
Okay, detective, time for a real case study. Here is a much more complex function with a whole bunch of different breaks. Let's see if we can use our new skills to identify every single one of them.
All right, our first clues are at x equals -4 and way over at x equals 2. See that abrupt leap from one solid point to another? Those, my friends, are classic jump discontinuities.
Now let's zoom in a bit, right on the x-axis where x equals 0. See that? It's not a jump, it's just one single missing point, that little hollow circle. That is our removable discontinuity, the pothole.
And last but not least, look what's going on over at x equals 3. The graph just plummets on the left side and skyrockets on the right, getting closer and closer to that invisible vertical line. That is our canyon wall, the infinite discontinuity. Case closed.
So this all leads to a really important question. Why should we even bother putting names to these things? I mean, why does it matter if we're looking at a pothole, a broken bridge, or a canyon?
Well, as the source material points out, this whole intuitive idea, this pencil test, is really just the visual starting point for one of the most important concepts in all of calculus, the idea of limits. Understanding these breaks is your first step into that much deeper world.
And I'll leave you with a final thought to chew on. Think about that removable discontinuity again, the pothole. Even though the point itself is missing, the graph from both sides seems to agree on where it should have been. So what value is that function approaching at that exact spot? If you can answer that, you're already on your way to understanding limits. Thanks for joining the expedition.